So in this video, we are going to have an introduction or like a overview of the attention mechanism in transformers using spreadsheets. So this is actually the end goal, and I want to cover this step by step. And my goal is to both cover the multi-head attention with two heads, but also multi-head attentions with, sorry, this is with one head and also with two heads. And the main advantage of implementing this on spreadsheets is that we have this instant gratification of checking how the output looks like when we change something. For example, I can change here the linear weight, some kind of linear weights for something, and then I can see what's the impact of this in the output. And yeah, but let's start from the scratch first. And then for this, first I want to illustrate an example of translation. And in my case, we will be doing what we call here this cross attention, which is this part here, in which we assume that we have as input a sentence, which is like the original sentence. In our case, it would be a sentence in English. And here we have the goal of always predicting the next sentence and the next word in a sentence, the translated sentence. And here, this is the core mechanism in which it compares like the memory from the original sentence and with this self-attention that we have here with those embeddings that we have from the sentence that we are trying to translate. So let me first add our example here as input here, as like our original words. We will be like, we'll have this small English sentence, I am happy. And as output, I will be translating this to Portuguese. So in Portuguese, we'll be using those two words for translating. Here on purpose, I am using I am as translation for so, and happy here means feliz. And let me just also place here that this is going to be our input and this is our output, which is the same terminology that we have here, inputs and outputs. And the way that neural networks, they represent words is by using vectors, or we also call embeddings. So the embeddings is like a vector representation of a word in which is learned by the neural network itself. And usually this vector representation is like grouped by giving like the semantic of the words. So the most similar the words are, they will be placed near to each other in the embedding space. For this example, we have, for example, the word I, am, and am. They are more similar than the word happy. So for like this reason, I'll be placing here, for example, the word I and am. They will be more like to the left, and the word happy will be more to the right. In a real scenario, the embedding space is going to be like multi-dimensional, like hundreds of dimensions, but here for visualizing I'll be doing just 2 dimensions. In the paper we have somewhere, yeah, here it's mentioned that in the paper the original dimension is 512 dimensions here for the embedding space. And here I'm also going to place the embeddings for the output. In this case, like for the word so and for the word feliz, and this embedding is coming from here. And in both cases, we have already those words in which they were already like they had some transformations here, but they still are like embeddings. So for example, here from this input embedding, after we pass through these layers, we have a embedding here that has more information about like the context of the sentence. So while here we have like information for each separated word, all of those words combined in a sentence, then they create this new embedding. And here the same thing. But now here the idea is actually we want to do this cross attention of those two embeddings, one like from the input, which we call memory, and the other is from the output. And our goal here is to have as output from this cross attention an embedding like that represents this output, but also gets this information that we got from the memory. And like the main intuition here is that there is a video from Serrano Academy that gives like this cool intuition, planetary intuition, in which the idea when we do this cross attention is that the similarity among words, like the new position, is going to be pushed based on the similarity. So in this case, since we are going to use this embedding as query and this as key and value, we'll see like those words will be sent closer to those words because it's more similar, and here the feliz is going to be sent closer to happy. That's what we expect. And in the paper we have here the like two implementations. First they introduce the scaled dot attention, and then they show like generic version, which is this multi-head attention. We'll start with this scaled dot attention, and then we expand to the multi-head here. So for the scaled dot attention, we can see like that in short we have just a single equation that allow us to get this attention, but they require here three terminologies, which comes from information retrieval, which here are the query, the key, and the value. In the cross attention, we'll have our output sentence. They are going to be our query, and both the key and the value, they will be our inputs here. And the idea here is that with this query and this key, we'll be doing like kind of similarity vector that we multiply by the value in order to get this new vector from the query. So it's like we are transforming this query into a new vector, giving the similarity that we have with this vector represented here in the key. So let me demonstrate here in this spreadsheet. So first we need to declare those three variables. As I said, like our goal here is to transform our query into a new vector. Let me just invert the color. So I inverted here just to make it clear that this is our like inputs that they go here, and this is our output. So the first thing we will do, like we have here this equation. Let's place here what we need, and here what we need is actually to do this softmax equation between the key, query, and value. But first let me declare here those vectors that we'll be using. So here for the query we'll be using our output, and I'll be using the array formula to just send this vector here. And for both the key and the value, we'll be using our input here. So let me place, in this case, we need to transpose. So let me call here transpose this. And here I just need to place the very same vector here. And the first thing we need to do here is to perform this multiplication, this matrix multiplication, which is an approximation of the cosine similarity. So what's happening here in this dot product is kind of mapping of the similarity between the words that we have in the query and the words that we have in the key. So let me perform this multiplication here, and as output here, since like this word so is closer to I and M, we can see that the similarity here is higher for both I am than for the word happy. And happy, we see here a higher similarity with the word feliz. And after this, we need to multiply this, and first we also need to divide here by the square root of the dimension. The reason this is happening is because if we have a very large dimension, those values tend to be giant, and the gradient would tend to explode with very large values. In this case, we have just 2 dimensions in our vectors here, so we just need to divide this by the square root of 2. So let me just implement here, and done. Now we have this scaled, which this is the operation that we see here in the image, is this part here. So we just performed this matrix multiplication, and then we did this scaling. This mask that we see here, this terminology, they are used in this part here, in which they don't want like the future words to be seen before, like, because the idea is always to predict the next word. So that's where this mask comes. In this part here, in the cross attention, it's not needed. So let me go back, and then the next step here is to perform this softmax here. This softmax is just like a transformation of all of those words into positive words that sorry, not words, numbers, positive numbers that will add to 1. And the goal here is like to now like use this similarity and combine with this value to create our new vector, which is going to be based on the contribution of those similarities. So let's calculate here. The formula of softmax is based on the exponential value. Why do we apply exponential here? Is because we want to convert all of those values into positive amounts. So as you can see now, this is all of this is positive, and then the idea here is to divide each one of those numbers by the sum of them in each row. So here I want to divide this by 3.8, and this I want to divide by 3.7. I can do this here directly by dividing this by the sum of the exponential of this. So I believe now this is correct. Let's see. Okay, so and here I'll be doing the same operation. Okay, done. So and now the way we can interpret this is percentages. We can see that all of those amounts, they sum to 1, and we see that for this first embedding here for the word so, we can see that they have this 64% of similarity with M, the word M, and 30% with the word I. And now, like, we'll have an updated vector which will be based on those similarities. And in order to create our new vector, which is the output of the attention based on those similarities, we needed to multiply our original like input vector to those similarities. So the idea here is kind of we're telling how much of each vector we want to use to our new vector. For example, here let me do step by step the multiplication here of this first dimension here of I am happy, which I'll be multiplying here to this portion here. So I would, for example, here use 30% of the amount of the word I, and then I will also use 70%, sorry, 64% of the vector and the word M, and I'll be using like 0.07. So what I'm doing here is like a step-by-step matrix multiplication. And here we can see that the word so, it went from 0.04 to 0.4, it went to 0.7. It went in the x-axis a bit to the left. And let me do this same for this. Here I would multiply this here and this, yeah. It's this part. I would multiply also. I would get 30% here, and then for this amount 64, and then for this amount I would get 1.4. And this, let me now display how this would look like in the chart. Let me select this. And now, since there is this similarity between I and M, we can see that this new vector, the embedding of the word so, was sent to more like closer to them. And let's see what happens here for the word feliz. So here let me just do the matrix multiplication instead of doing step by step, so that we can see the output of both of them. Let me remove this, and done. So in the word feliz here, we can see that it's using like 30% of the word I and the word M, and 70% of the word happy. And done. This is what we call scaled dot attention. We just finished here the implementation. Now I want to expand this implementation into the multi-head attention, which is what we have in the original implementation. And the main difference here is that this scaled dot attention is a portion of the multi-head attention. And the main difference is that we apply a linear network. It's just a densely connected network before, like, or better actually after each one of our input vectors, the value, the key, and the query. So like the equation here is very similar to the equation of attention, but now we just need to multiply those three vectors here into in the input in order to have this. And the idea here is that by having this linear, this densely connected layer, we can create multiple versions of this vector here. And then in the end we can concatenate all of them. And also the idea of using here linearly connected layers is that we can change the dimension of this output and then concatenate all of them in order to regain gain the original dimension. For example, in the original paper, they split into 8. They use like the number, the dimension that they use for each one of those weights is like the original dimension. This would be the number of rows, and as number of columns they divide by 8, so it would be like 64 for each one of the heads, because in this way they can concatenate all of those 8 heads in order to get this original dimension. The idea here is closely similar to our case. We could have, for example, 2 embeddings that could be concatenated, which I'm going to show here in a bit. But first, let me just implement here this portion. And here the only difference is that we just need those 3 vectors that needs to be multiplied, and the dimension of them is going to be in once, like there would be the same dimension of the number of embeddings. I have the number of embeddings in one side, and the other side it would be the number of heads that you want to create. If in this case, in this first example, I'll not be doing any concatenation. It's like I'm creating just 1 head. But if I wanted, for example, 2 heads, then it's the example that I have here. Let me find here. Yeah, it's the example that I have here, in which what happens here is that my output attention, instead of having this semi-dimension of my output, if I have just 1 column here, then the output also will have 1 column. And then in this case, I need 2 heads here, because then I'll have 2 outputs, and then finally those 2 outputs, they can be concatenated together, and then finally we have this output that again represents this embedding from the input. So this is this idea of using multiple heads, but they have to be proportional here with the number of dimensions. But so let me implement here this example using just 1 head. The implementation here is pretty straightforward, and in practice those numbers would be like weights from neural networks. Here I'm using a identity matrix just to initially not have any impact in the output. And here the only difference is that now in the key, query, and value, instead of having our like input output vector, this is my example. So instead of having my output here and having here my inputs, instead of this, what I'll have here is this product of the query and the weights. So my original query here is the output, and I'll do here a matrix multiplication of my original query with the weights here for the query. And then here I need to do the same, but now here for the key. So instead of having the key, now I have this matrix multiplication of my key and the weights for the key, which is this second part here. And in this case we need to transpose, and then finally here I also have the weights for the value here, which I will be multiplying. So let me calculate here matrix multiplication of also my inputs and the weights here, and now like this is just like a linear transformation to like send like those original embeddings to different shapes. And here we can even like visualize what would be the impact. For example, Let's first change here the weights that are like connected with the query. The query here is our output, and if I have, for example, here instead of 1, let me put 1.5, and also let's visualize what would be this output. So here I'm going to place this vector here so that we can visualize. So we can see here that when I changed from 1 to 1.5, it's like we are like doing some linear transformations in this output word here. And also let me also put here the legend what we have here. This is our transform, this is our attention model, and now let's see what happens if I do like some transformations in this second. This second weight here is directly connected with the input word here. Let me, for example, change here to 1.5, and also let me place here how it looks like the transformation. So I'll put here this transposed of to reverse it back to the original values, and here let me also escalate this here so that we can visualize all of them. And okay, so when I did this change here from 1 to 1.5, for example, now we're doing a transformation with those input words here. And let's see, for example, if I do a transformation here from 0 to 0.5, or for example here 1 to 1.5, I'm going to send to different directions. And then finally this vector is something that is multiplied here, so the changes will be more connected with the output vector. So for example 1.5, we can see that there are big changes in this in actually the attention itself. And that's it. So here we did I demonstrated this implementation of the multi-head attention using spreadsheets, and the only portion here that is missing is here in the very end. Let me get in this example with 2 heads. After this concatenation, we can also have another linear layer here, which will have this same dimension of the number of embeddings, but it's still like just a densely connected layer. But the main idea here is already implemented here, and with this idea of doing this transformation based on similarity, the transformer and the attention mechanism is very powerful into acquiring context. Doesn't matter how far or how close is a word in a sentence, because it's going to pretty much look all of the words and compare either like with the memory in this case for translation, or with themselves. So that's it for now. I hope you guys enjoyed, and this spreadsheet will be attached in the video. And yeah, bye bye.